Welcome back. Today we're going to continue our discussion on molecules and how to properly draw them. In our last lesson, we learned how to draw Lewis structures, which is a two-dimensional representation of the chemical structure of a molecule. However, molecules exist in three dimensions, and we need to account for the geometry of the molecules to properly represent them. That's what today's lesson is all about. And we're going to learn this method called VSEPR, which is short for valence shell electron pair repulsion theory, which is a really easy way to figure out what the geometry of a specific molecule is going to be based off its Lewis structure. At the end of this lesson, you'll be able to make use of this handout to help you solve any problem that you come across, whether it's in this class or a future chemistry class. So let's go ahead and get started. So this theory was put together by these two chemists, Gillespie and Naholm. And the basic tenet of this theory is that the electrons that are in the valence shell like to be as far away from each other as possible because electrons naturally have a negative charge and want to repulse each other. Now we know that two electrons can fit in each orbital, and each electron can be either spin up or spin down. So those electrons are going to be in a similar region as the other electron in that orbital. However, the arrangement of the orbitals is in x, y, and z dimensions. So we can expect that the molecule will space itself out such that the electrons are as far away from each other as possible. Now we're going to make some geometric arguments in here. And the next lesson, which is on molecular orbital theory and valence bond theory, will help us understand why some of these orbitals arrange themselves in the way that they do. But for now, we're just going to kind of learn how to figure out what the shape is based off these simple principles. One thing to keep in mind is that there are two types of electrons that are in a molecule. There are the electrons that are in a lone pair, and then there are electrons that are in a bonding pair. The electrons that are in the bonding pair are localized between two atoms, and those electrons have a slightly less diffuse field than the electrons that are in a lone pair. Therefore, the lone pair interactions that are going to occur will cause more repulsion than a bonding pair interaction. All right, so we're going to consider both these bonding and lone pairs when we do this. And what I'm going to use is this website. So it's really helpful to visualize each of the shapes. And we're going to start here by looking at some of the simplest molecules that can exist and what their shapes would be. The simplest molecule is a diatomic molecule, which would be just two elements bound together. And let's see here. So a couple examples of that would be carbon monoxide, cyanide, hydrogen chloride. And when we look at these structures, there is really no geometry occurring because just the two atoms are like 2 points, and between them are the bonds that exist. Now, hydrochloric acid also has, each of these also has lone pairs on here, which I think I can get them to be shown. Maybe not in these ones, but they're not really going to be affecting the geometry in this case, because there's only one way that we can arrange these atoms. If we go on to add 3 atoms, and this is where we're going to start, those 3 atoms can be arranged in a line, or they can be arranged in a different geometry. If we take a look at carbon dioxide, which has a carbon and 2 oxygens on either side of it, we see that this molecule is linear. That is, if I look down one end of it, I can't see any other atoms. Now, if I go to add a fourth atom, there is another type of geometry that can exist. And what we would normally expect is that these electrons would be wanting to arrange themselves such that they're as far away from each other as possible. And it turns out to be the case. That's the case when you have a 120-degree angle between each of these bonds. So I have boron trifluoride here, and the fluorine atom is a little bit smaller than the boron atom because it's to the right of it on the periodic table. And we can see that there is 120 degrees between each of these bonds. All right, so this is known as trigonal planar geometry. So you can see that here, trigonal planar. And this website makes use of this AXE notation. Let's go back to my notes and let's look at each of these notations here. All right, so far we've looked at linear and trigonal planar geometries. There are a couple ways to represent the geometry, and it all starts with figuring out the steric number, which is the number of bonded atoms that are attached to that central atom, plus the number of any lone pairs on the central atom. When the sum of those two numbers equals 2, that's a linear electronic geometry because there's two bonded atoms and there can't be any non-bonding lone pairs there, so that would be 0. The bond angles will be 180 degrees, and I give you a couple example molecules to remember what the geometry should be. But the other notation is this AXE notation or AX notation, where, and I have it on my sheet here. I don't have it on my sheet. I have it down here. Let's see. M and N. I just want to make sure I use the correct notation. So if we assign this the letter M, the coordination number, and then the number of non-bonding lone pairs N, each of these molecular geometries will have a unique AX notation. So for linear, this will be AX2. For trigonal planar, this will be AX3. Now, one thing that can happen is instead of having 2 atoms on this central atom, or 3 atoms on the central atom, we can have 2 atoms and a lone pair. So what that'll look like is, here it is. For example, sulfur dioxide has this type of bent geometry. Another molecule that has this bent geometry is ozone, O3. So in this example, if I show the lone pair, that's here in orange, we can see that this molecule still has that 120 degree angle here. The angle between these bonds, these double bonds, is going to be approximately 120 degrees. It will be slightly less than that though, because this electron up here is a lone pair, and lone pairs affect the bonds a little bit more, so they push down more, and this is going to cause the angle between these two bonds to be slightly closer together. So what we'll see on here is that I list that the bond angle between the oxygens is slightly less than 120 degrees. As we get to a bigger and bigger atom in the center, that will have a larger and larger effect. So the bond angles will get smaller and smaller. All right, so this notation would be AX2E for 2 bonded atoms and 1 lone pair on the central atom. So the A just represents the central atom. Now, if we move on to 4 atoms attached to the central atom, there it is. we can begin to get these electronic geometries that are called tetrahedral. And there are three molecular geometries that can arise, where we either have 4 atoms, 3 atoms and 1 lone pair, or 2 atoms and 2 lone pairs. If we start with the simplest examples, tetrahedral, we can look at methane. And one thing that we know is that it doesn't have the same geometry that is drawn in a Lewis structure. So in a Lewis structure, we would draw all these hydrogens as 90 degrees away from each other. But clearly from this image, we can see that it's not 90 degrees, it's more than 90 degrees. And so in 3 dimensions, these hydrogen atoms can space themselves out so they're about 109.5 degrees, where each of these hydrogen atoms is the point on a tetrahedron, which is why these are called tetrahedral electronic geometries. Another example of this is carbon tetrachloride. Here we can see that the carbon chloride bond is slightly longer, and the molecule still has the same geometry. If we instead replace one of these atoms with a lone pair, like in nitrogen trifluoride, we'll see that the geometry pretty much stays the same, just one of those lone pairs is invisible. We typically can't see lone pairs with modern methods. If you had a crystallography device, you could see the atoms, but you wouldn't be able to see the electrons. So typically we represent the molecular geometry, the name trigonal pyramidal, for what we would observe if we couldn't see that lone pair. However, that lone pair is still affecting the overall geometry, causing this to be distorted so it's not trigonal planar, but is instead 109.5 degrees. Well, I guess in this case, slightly less than that, but still not a trigonal planar geometry. It's a trigonal pyramidal geometry. So each of these has a unique name. They mean different things. The chlorate polyatomic anion has double bonds because chlorine is one of these elements that can have an expanded octet. So here we have another interesting example of trigonal pyramidal. The last tetrahedral electronic geometry is the bent geometry, which is how we're going to represent water. So water, if you draw it like this, you're not going to account for the unique properties of water, which come about from it being bent. We'll talk about in this lesson about molecular polarities, which is the sum of all the bond polarities in a molecule. And we'll see that water is very polar, and it's due to its 2 lone pairs and oxygen, causing the distortion of the bond angle between the oxygens and the hydrogens to be not 180 degrees, but less than 109.5 degrees. For water, it's approximately 104.5 degrees. So we need to remember that water is bent. And let's go and fill out these X notations. So here we have 4 atoms attached to the central atom and no lone pairs. So we can just write this as AX4. For this trigonal pyramidal molecular shape, we have AX3E. And then for the bent shape, it's AX2E2. At this point, you've learned most of the important geometries for simple organic molecules. However, there are some other ones I wanted to talk to you about today. These are the shapes that come about when you have coordination number 5 or 6. And all these are grouped under either the trigonal bipyramidal or the octahedral electronic geometry. And when you want to try to fit 5 atoms or coordinate, 4 atoms and a lone pair, for example, around a central atom, we have to do it a little bit differently than you might expect. So if we take a look at the simplest example, phosphorus pentafluoride, we'll see that they don't arrange themselves in one plane around the central atom, but instead there is two atoms that are in a line, and then there's a plane perpendicular to that. So here we have, if I orient it this way, we have two directions that we can represent. The three atoms that are in the same plane are called the equatorial atoms, and then the two atoms that are vertical, perpendicular to that, those are known as the axial atoms. So we have axial and we have equatorial. So we'll use that same example, phosphorus and pentachloride. All right, so these are my axial atoms. And then I have the other atoms here. These ones are my equatorial. I want to make sure I write this right. Equatorial. And the angle between the equatorial atoms is going to be 120 degrees. So we have two different bond angles. And then the angle between the axial atoms is going to be 180 degrees. Well, I guess we look at the angle right here between these ones. So this would be 90 degrees. All right, so we have two different angles that we can represent. And the next thing that will occur if we were to remove one of these atoms is that we'll see we can either remove an atom from the equatorial side or the axial side. And it always gets removed from the equatorial atom first. So the equatorial atom gets removed. And the reason why is those electrons that are in that bond can affect two atoms here. They can, so yeah, I guess like the electrons that are in the equatorial atom can affect the atoms that are either axial, so the top two, or they can, or if we remove the top atom, then it will affect all three of the equatorial atoms. So it's preferred to only affect two of the atoms. Therefore, the equatorial atom is always removed. And we can see that with sulfur tetrafluoride, where if I orient it like this, I think that's the easiest way to see it. Those axial atoms are still there, but one of the equatorial atoms has been removed. And then if we get to the next example where we have two lone pairs, like in chlorine trifluoride, two equatorial atoms are removed. And then we end up getting this interesting T shape here. So it looks like a T if we flip it this way. The last one was called a seesaw shape. And the reason why this is a seesaw is if you put it like on the table, it'll like seesaw back and forth. I think you can kind of see it there. So if you push down on one end, it'll go back and forth like a seesaw. And then if we remove three lone pairs, then we're just left with the axial atoms. So xenon difluoride. The lone pairs are not shown; they're drawn in here. But those would be all the equatorial atoms removed, and then you're just left with two axial atoms. And then the bond angles here are going to be just 180 degrees from each other. So I actually found this picture on Wikipedia. shows that. Okay, so the notations here, we have this one is AX5, this one is AX4E, T-shaped is AX3E2, and then linear is AX2E3. All right, the last set of molecular shapes is for the octahedral class. And the simplest way that we can arrange 6 atoms is by 6 points on an octahedron. And when this occurs, we have 4 atoms that are in the same plane. But if we go and we flip it the other way, it doesn't really matter. So you can see it, four atoms there, 4 atoms there in the same plane. Each of these are going to be 90 degrees away from each other. And there's a lot of different molecules that actually have this octahedral notation. It's very common. Sulfur hexafluoride, tellurium hexafluoride, the aluminum hexachloride anion are just a few examples of that. If we go to remove one more electron, remove one atom and replace it with a lone pair, we end up getting a square pyramidal structure, which looks like this. And this will distort the geometry of these angles so that they are going to be slightly less than 90 degrees. So it'll push these atoms up a little bit. It's not shown all that well there. So that's this octahedral and this square pyramidal. And then there's one other one that can exist. It's if I replace one more atom with a lone pair, we'll get the square planar geometry. And in this case, we remove another atom from the other side of the one that just got removed. So we'll remove this top one. And that's to minimize the electron-electron repulsion. And we end up getting this specific shape, which is called square planar because it's a square in a plane. And that's an easy way to see it right there. So one plane, it's a square. I looked into it. There is no other geometries that physically exist. If we were to remove more atoms and replace them with another lone pair, so I can conceive of an AX3E3 and an AX2E4 geometry. However, there's been no molecules that have those observed geometries, which I think is very interesting. So we'll stop there with square planar. And that would be AX2E, this should be AX5E. This one's AX4E2. And then I'll write down over here, AX3E3 and AX2E4 don't exist. And one way I told you that we can rationalize why some of these central atoms can have expanded octets is because they're in the third period or greater, and they have access to d orbitals. When you have an electronic geometry with a coordination number of 6, we're only making use of 2 of those d orbitals. So there actually are some rare instances where we can make use of a 3rd, 4th, and even a 5th d orbital, and then we're out of d orbitals and we're out of luck at that point. Those electronic geometries are called pentagonal, bipyramidal, square, antiprismatic, and tricapped trigonal prismatic. And there are a variety of other minor other cases as well. But these can be possible when you have very large atoms like iodine, tantalum, and rhenium. So we don't need to worry about those for this class, but if you study inorganic chemistry, you might be interested in an atom that has some interesting geometries, and I thought that'd be interesting to point out. Now, how do we find the molecular geometry? This is what we're going to spend a lot of the rest of this lesson doing, is just playing around with drawing some Lewis structures and determining what the molecular geometry is. We'll make use of this handout. I'll show you how to use it. So let's go ahead and just pull this up. We'll start by drawing the Lewis structure for these molecules. And if it's a diatomic molecule, it only has 2 atoms. It's definitely going to be linear. If it has 3 or more atoms, then we have to look at this chart here. Now, we'll always want to count the number of electron groups that are around the central atom, because those will impact the molecular geometry. And if a group of electrons is always defined as a bond or a non-bonding electron pair. One important note here is that triple bonds and double bonds always count as one group for the purposes of this VSEPR theory. That's why you'll see that I arrange this as bonded atoms rather than as number of bonds. Based on the number of groups around the central atom, it'll fall into one of these 6 basic categories. And then within each of these categories, there are a number of different names for the shapes, depending on how many of those atoms and lone pairs there are. We'll start with beryllium dichloride, which has 16 valence electrons, 7 from each of the chlorines, and then 2 from the beryllium. And beryllium, if we remember from the last lesson, is one of the exceptions where it only has 4 shared electrons. It's electron deficient. It's going to only have 4 electrons. We can't fulfill its octet. And because of that, we can see that the geometry that fits best is going to have 2 atoms that are attached and 0 lone pairs. So this will be in a molecular geometry that's linear. What I'm going to do is I'm just going to list molecular geometries. The electronic geometry will also be asked for sometimes, but I'm going to be specifically talking about molecular geometries for these problems. We can also list the bond angles here. So these ones are going to be 180 degrees from each other. Another simple example is boron trichloride, which is another octet rule exception. And the proper way to draw this one is where the chlorines are as far away from each other as possible in a plane. So this would be drawn like a Y. And then you can put the lone pairs on the chlorines, but there's no lone pair that's left over for the boron. So here we have 24 valence electrons that are all used up. This comes out to be trigonal planar. So it has the AX3 notation. And this one is AX2. The bond angles here are 120 degrees. All right, so if I have this molecule, sulfur difluoride, which has 6 plus 14 or 20 valence electrons. When I go to try to draw this one, if I were to put the fluorines on either side and distribute the electrons, we would get this Lewis structure. But what we want to do is, instead of drawing the Lewis structures here, we want to try to draw the molecular shapes. And this would be the incorrect way to draw the molecular shape, because these lone pairs are going to influence the geometry of the shape of this molecule to make it a bent molecular shape. So 2 bonded atoms and 2 lone pairs make this the wrong way to draw this. So I'll just put this in the corner and say this is not right. And we'll fix that. But moving the sulfur up, I'm just going to redraw it because it's easier. And the easiest way to draw these shapes is where you just draw like a V, and then you put the lone pairs like this. There's another way we can draw this, where I can use the wedge and dash notation, where the wedge refers to atoms that are coming out of the plane, and the dash refers to atoms that are going into the plane. So I drew it up, upside down, doesn't really matter. But yeah, you can draw it this way as well too. And then these bond angles are 109.5 degrees. But in this case, it's going to be slightly less than that. Probably significantly less than that, because sulfur is fairly large. So this is going to be less than 109.5 degrees. So we're just going to do a lot of examples. So feel free to jump ahead and try some of these on your own. That's really the best way to practice this. And I have a lot of problems at the end that I'll go through as well. So we'll do like a subset of all of the different geometries here, and then work through some more after that. Ozone is a really important molecule, and it has an interesting shape to it. The 3 oxygens are not in the same line. And this one is a little bit trickier to draw because there is a resonance structure for ozone. Oxygen has 6 valence electrons, so 3 of them would be 18. And what we'll try to start doing is start by putting the oxygens in a line. And if we do this, and try to distribute all the lone pairs like such, this will end up giving us too many electrons. So in this case, we know that we need to have a double bond. So this one is incorrect. And then one other thing to note is that because we're going to have a double bond, we're going to have one alone electron pair on the central atom. So at this point, we might go ahead and look ahead at the shape and say, well, if it's going to have 2 atoms attached and 1 lone pair electron, this is going to be a bent geometry. So I'm going to want to draw it as bent. So in that case, this is going to be AX to E. We'll put one lone pair there on the oxygen, which then affects the shape of this molecule, making it bent. And then one of the oxygens will have a negative charge. And then this oxygen here will have a positive formal charge. So that's good to go back through and practice that. In fact, why don't we do that real quick? How did I get the positive and how did I get the negative? The positive came about from taking the valence number, which is 6, and subtracting the number of lone pair electrons, there's 2 of them, and then half the number of electrons in the bond, which is 3, giving us a positive 1 charge on that central oxygen. And then you can do the same thing for that oxygen, which would be 6 minus 6 minus 1, giving you a negative 1. And there's actually 2 resonance structures that we can draw. And the bond angles here are going to be slightly less than 120 degrees. Now, one thing that's interesting is these are both called bent geometries, but one is tetrahedral bent and the other is trigonal planar bent. So do keep in mind that some of them have the same name. For example, the linear molecule that we drew here, there's another geometry down here that's also called linear. So those, I think, are the only ones that are the same. Yeah, so there's 2 linears and there's 2 bents. Silicon tetrahydride is a simple molecule to draw. Silicon has 4 valence electrons, and then hydrogen has 1 each for a total of 8. In this case, there's really, this is kind of like drawing carbon in the middle, but we're going to have silicon instead. But the one thing you want to pay attention to is how do you draw the hydrogens around the silicon? Well, you can draw it this way if you're doing Lewis structures, but we don't want to try to draw Lewis structures here. We want to draw the shape. So we're not going to draw it this way because that falsely represents the hydrogens as being 90 degrees away from each other when they're in fact 109.5 degrees. So what we'll do instead is we'll put 1 hydrogen up. We'll put 1 hydrogen slightly to the side like this, kind of like a bent geometry. And then another one of those hydrogens will be on a wedge. And then the other hydrogen will be drawn here as a dash down. Here this represents a 3-dimensional 109.5 degree geometry, which is tetrahedral. It takes a little bit of practice, but that's how it's typically drawn. And this is a AX4 notation. Excuse me. The next one is PCl5. Phosphorus has 5 valence electrons, and then we have 35 from these chlorines for a total of 40. For this one, we're going to arrange the atoms, and it either is going to be one of 2 geometries. It could be square pyramidal, or it could be trigonal bipyramidal, and that depends on how many lone pairs there are on the central atom. So in this case, if I distribute all the electrons around the chlorines, we'll end up getting 8 times 5, which is 40. So we'll end up getting the AX5 notation on this one. It takes a little bit of practice to jump ahead like that in your brain, but it is in fact AX5, and we can verify that. When we do this, I want to draw 3 of the atoms as being equatorial. And the easiest way to draw that is to put one on a wedge, one on a dash, and then one here off to the side, and then these 2 up and down. That's going to trick our brain into thinking this is a trigonal bipyramidal geometry. And we have 2 sets of angles. The angle here is 90 degrees, and then the angle here is 120 degrees. Doesn't quite look like that from the picture, but that's again, because this one's going out into the plane, and this one's going out of the plane. What else is there I want to say about this one? I guess it's trigonal bipyramidal. The reason why it's called that, and I always forget how to spell bipyramidal, is because it's shaped like a triangle, and then there's a pyramid on the top and a pyramid on the bottom. All right. The next one, bromine trifluoride. One of these halogenated compounds. For this one, each of the halogens is going to contribute 7 electrons for a total of 28. If we go ahead and distribute the fluorines around the bromine, they'll each have 3 lone pairs, because fluorine is always going to have a single bond. It never wants to have double bonds. And we'll have 8 electrons for each of those. 8 times 3 gives us 24. Therefore, we need to have 2 lone pairs on the central bromine, because we have 4 electrons left over. In that case, we're going to have the AX3, because there's 3 atoms attached, E2 notation. AX3E2 is T-shaped. T-shaped comes about from removing 2 equatorial atoms. And we'll start by drawing the bromine in the middle, because it's less electronegative. We'll put the 2 fluorines that are on top here. And then we'll draw 1 fluorine off to the side. This is your 1 remaining equatorial atom. And then we have 2 lone pairs, which we'll draw like this to kind of represent where those chlorines would be here on this one. We don't draw the lone pairs as wedges and dashes. We just draw them right there on the bromine. In fact, they're kind of in these orbitals, like you can maybe think about it shaped like these lobes. Yeah, so I sometimes draw it like that. And I want to emphasize those are affecting the geometry here, because what we normally would expect is that these fluorines would all be 90 degrees away from each other, but this is actually pushing on these 2 atoms bonds, so it's actually pushing the electrons in this bond so that these are moved in slightly. So really, the proper way to draw this would be at a slight angle, because it's less than 90 degrees. So if we want to get really particular, we can with this really useful method that we're learning. So VSEPR is very, very handy. Instead of having to solve a whole bunch of complicated mathematical equations, we can just make use of these arguments here from geometry. And they align really well with the observations, and this is why everyone uses this method. All right, so what am I doing here? This is called T-shaped, my favorite geometry. It's not quite T-shaped, it's a little bent. It's less than 90. All right, I3. This has a negative charge here, so we want to make sure we include that. Iodine has 7 valence electrons, and then we add one more for a total of 22. If we put one iodine in the middle, we have to put the other 2 iodines either in a line or in a bent shape. But what we're going to see in this one is that each of those iodines is going to have 3 lone pairs, and we'll be left with 6 electrons left over. So this is going to be our AX. I don't have it written on here. This is going to be our AX2E3 notation. So when we distribute these electrons, we have 6 left over. Those 6 left over are going to go in the 3 equatorial spots. So we removed 2 of them, and we removed this third one. And when you remove that third one, all those electrons here are going to push equally on these bonds so that they are, in fact, 180 degrees now. That's an interesting fact. So, and then if we look at the formal charge on the iodine in the middle, 7 minus 6 minus 2 is going to give us the -1 charge that's on that central atom. Selenium tetrafluoride looks like it might have the same shape as silicon tetrahydride, but it doesn't. And that's because selenium is in the group as oxygen. So we have 6 plus 28, or a total of 6 plus 28 is 36. Wait, no, 34. Valence electrons. In this case, the fluorines are each going to have 8 total electrons, 6 valence, 6 lone pairs electrons, and 2 in the bonds. So 8 times 4 is 32, and it's going to leave us with 2 electrons left over. So this is going to be an AX4E notation. AX4E is seesaw. And when we have the seesaw notation, we've only removing one of those equatorial atoms. So I always like to start by drawing 2 axial atoms, and then I'll draw 2 of the equatorial atoms where one's on a wedge and one's on a dash. And then here's where my lone pair is going to go. We have 2 sets of bond angles here. These electrons are going to push on the axial atoms, and it's going to affect their geometry. So these are going to be now less than 90 degrees. And these atoms, these also get affected, I believe, to be less than 120 degrees. All right, so let's keep going. IF5. We can figure out how many electrons we have to start again. So 6 times 7 is 42. And then 8 times 5 is 40, leaving us with 2 electrons left over. So this is going to be an AX5E notation, which we haven't done yet. AX5E is down here. That's a square pyramidal geometry. The square pyramidal is where we have the octahedral geometry, but we just replace one atom with a lone pair. And I typically either draw it on top or on the bottom. And I like to do two sets of wedges and two sets of dashes here, showing that these are, and then one down here, showing that these are all in the same plane. There's a couple ways to draw this, honestly. But this is how I typically draw it. And sorry, my drawings are really terrible today. Maybe I had too much caffeine. Is there such a thing as too much caffeine? I don't know. I think there is. Single espresso this time. Okay, there we go. So this is the square pyramidal geometry. One of my favorites. I think it looks cool. The square pyramid. There's a pyramid on the bottom. In this case, pyramidal. I mean, if we flip it, it's the same thing, right? So, and then this lone pair is going to push down on all of these. So each of these angles is now less than 90 degrees. The last one I have for us is a pH 3 molecule, phosphorus trihydride. And that is, if you're paying attention, the only one we didn't cover yet is the trigonal pyramidal geometry. Because we need to give phosphorus an octet. It's not one of the exceptions. When we draw this one, there's a couple ways to do this. We could draw it like this. Or most people will draw it where we have put the lone pair on top and then the hydrogen like that. So here we have a bond angle that's less than 109.5 degrees. And it is trigonal pyramidal. It's a triangular shaped pyramid. Pyramidal. Cool. This is AX3E. And then we're done. So I've gone through, I believe, one of all these except for the octahedral. It's probably the only one I skipped. Yeah, so cool. Let's talk a little bit about bond lengths and strengths, molecular polarity, and intermolecular forces. When we think about the length of a bond and the strength of the bond, the length and the strength are going to be inversely proportional to each other. And it depends on how many electrons are shared between the two atoms. The more electrons that are shared between the atoms, the more orbital overlap those atoms are going to have. And we expect then a double bond is going to have more overlap than a single covalent bond, thus resulting in a shorter bond and a stronger bond. If we go on to add two more electrons in that bond, it becomes even more short and even more strong. If we look at some of the comparisons here between, close this out now. If we look at some of the comparisons here between a carbon-carbon single, double, and triple bond, as we increase the number of electrons between them, the bond length decreases by about 0.2 or 0.15 angstroms. And then the bond energy approximately doubles, or not quite doubles, but this one is close to doubling, and then this one is increasing by about 60%. So there's a significant difference in energy between a double and a triple bond than a single bond. We see the same trend for carbon and nitrogen. The bond length doesn't change as much between single and double, but it does a lot between double and triple. That's interesting. And then the bond energy jumps up significantly here. And then if we look at a carbon-oxygen bond length again is decreasing by about 0.2 then to 0.1 angstrom here. And then the bond energy increases substantially here, and then substantially again here, another like 300 kilojoules per mole. And carbon triple bond to oxygen is one of the strongest bonds that can exist. It doesn't occur all that often. This would be the carbon monoxide molecule. And so carbon monoxide is got this really strong energy between its atoms. Now, we can also look at the molecular polarity of a molecule. So if we have a molecule that is covalently bonded, it can either be polar or it can be nonpolar. And the overall molecule can also have a polarity as well. What we'll do is we'll sum all of the bond polarities together as vectors. So we'll treat them as going in one direction, and then we'll sum all of the x and the y components together so that we can get an overall molecular polarity, where I'm going to draw the bond polarity as going from the partial positive to the partial negative side. The textbook does it the opposite way. So it'll draw from the negative to the positive, which is how it's recommended to draw it. But I've yet to see very many people make that transition to drawing it that way. So I wanted to introduce it this way. The overall dipole, if there is one, is called the dipole moment of the molecule, which is given the Greek letter mu. And we want to pay attention to the overall shape, too, of this molecule. That can help us figure out really quickly whether the molecule will be classified as polar or nonpolar. For a nonpolar molecule, all these bonds are going to cancel each other out, all these dipoles for these bond dipoles, resulting in no dipole moment. And then for polar molecules, one end of the molecule is going to be more negatively charged than the other, resulting in a net dipole. We're going to make use of this molecular polarity simulator, but I need to go to the dentist, so I'll record this in a little bit. All right, so let's start by looking at hydrogen fluoride on the molecular polarity simulator. We have fluorine, which is the most electronegative atom, and then we have hydrogen with the value of 2.1. If we think about where the charges are going to be located, fluorine is going to have more of the electronegative charge. So if I look at the electrostatic potential, we see a lot of negative charge on this end of the molecule and positive charge on the other end. So if this was represented with a bond dipole, if we represent this end of the arrow as the positive charge, and the arrow point as the negative charge, this will go towards the fluorine. And then because there's just one bond in hydrogen fluoride, the molecular dipole is going to be in the same direction as the bond dipole. So we'll have to sum all the bond dipoles to get what the overall molecular dipole is. Another way of looking at this is with the partial charges. So in a compound that's an ionic compound, we'll have a full positive and a full negative charge. But here we have about a 0.4 positive charge and a negative 0.4 charge. so our bond dipole and molecular dipole go in the same direction here. They go towards the fluorine. Your textbook does it so that it goes the other direction, which is in line with physics notation. But a lot of the chemistry books and stuff that I've read do it the other way, so we'll do this notation. And then we'll say that this is an overall, the bond dipole and molecular dipole are in the same direction toward fluorine. Overall, this is a very polar molecule. If we looked at just a simple diatomic molecule like chlorine, since these are the same element, there is going to be no overall bond dipole. So therefore, this is a nonpolar molecule. All right, so let's look at a different molecule. It has more than 2 atoms, like carbon, tetrafluoride or tetrafluoromethane. And carbon is much less electronegative. So what we're going to expect here is that the bond dipoles go towards each of the fluorines. We'll have 4 overall bond dipoles. And because these are points on the corners of a tetrahedron, it turns out that each of these bond dipoles will cancel. It's kind of hard to see that even in 3 dimensions. But if we click the molecular dipole, we won't see anything pop up. And that's because all of these components are canceling each other. Although there is a partial charge on these fluorines, and we can see that here with the electron density, we're going to have more electron density on the fluorines than in the middle of the molecule overall. And you can also see there's a little bit of a negative charge there. Overall, this is not a polar molecule. And let's remind ourselves on how to draw a tetrahedral molecule. We're going to put one of the atoms up, one of the atoms in the plane over here, one of the atoms out of the plane, and then one of the atoms into the plane. And then I'm going to add my lone pairs. And there is no molecular dipole because the bond dipoles cancel. If we take a look at another useful molecule, ammonia, which is NH3. Reset this. Which direction do you think the bond dipoles are going to go in this case? What if we add the electronegativities here? All right, so in this case, we're going to have the bond dipoles go towards the middle because hydrogen is less electronegative than nitrogen. You can see that here with these spears going towards the middle. And when I go to, before I go and look at the molecular dipole, let's draw the Lewis structure. So there's overall 8 electrons that we can distribute, 8 valence electrons. One of those is going to go on the nitrogen. And that's my cat. She wants to go outside. Hi, Hemingway. We can go outside after this video. All right, so here I have one lone pair that I need to account for, and it's going to influence the geometry here. So this becomes a trigonal pyramidal geometry. We can see that up here. This is an AX3E molecule. And then in this case, because that lone pair is there, these bond dipoles don't cancel because we're not in a single plane. The X and the Y component will cancel, but the Z component won't. And so we'll get an overall molecular dipole that goes through the middle of the molecule towards the lone pair. We can see that this molecule is very polar. Got a large lobe of negative potential above the molecule, but where the lone pair is. Another really useful example is to look at one where there's 3 different types of atoms. So chloroform has 1 hydrogen and 3 chlorines attached to a carbon. In this case, 3 of these bond dipoles are going to go towards the chlorines, and then one of the bond dipoles is going to go towards the carbon because hydrogen is less electronegative. So it's a little hard to see that here on this molecule. What about trifluoromethane? It's a little bit easier to see these arrows here. So in this one, we're going to expect that there is not going to be complete canceling of the molecular dipoles. And this is going to actually look pretty similar to ammonia, but in the opposite direction, where the molecular dipole is going to go through the molecule towards the fluorines. And so we'll see a large negative electrostatic potential on the bottom of this molecule. Okay. H2O. Remember, we have to put 2 lone pairs on the oxygen, and that's going to cause this geometry to be bent with 109.5 degree angles, and actually slightly less than that, about 104.5. But anyways, so these lone pairs are pushing down on the bonds, and what we can expect here is it's going to have a bond dipole towards the lone pairs, like it is in ammonia. And we get a very polar molecule, which is why water has very unique properties, because it's a universal solvent and it's polar. So we can see that here. All right, one other molecule that's really useful to play around with is this oxygen difluoride. So oxygen difluoride is going to have a very similar structure that water has. But what's the big difference here? Well, fluorine is way more electronegative than hydrogen is. So in this case, the fluorines are going to, so we have, okay, let me draw it this way. So we have bond dipole here, bond dipole here, and then we have these the electrons here. So in this case, I would suspect that you're probably going to get a dipole that goes in a molecular dipole that goes in the reverse direction as water. It's hard to know exactly what the strength is here because we do have these electrons. I don't think this is an example on this software, but there's other software that's out there that'll predict for you what the strength of that dipole is, and this is known as the dipole moment, and you can actually get a number that's represented by the strength of this arrow, the magnitude of it. All right, so let's close off this lesson by learning a little bit about some different types of bonds. This isn't talked about until chapter 15 in the textbook. I think this is a little late to introduce this topic, and we won't go into too much detail on it, but it's about the bonds that occur between molecules. What we've been talking about so far are the bonds that occur within a compound or molecule, like an ionic bond and a covalent bond. But there are these forces that exist between molecules that are intermolecular, not intramolecular, and they cause a lot of the properties that we're interested in. And so let's look at the differences here. So I have an ionic bond where I have a negative charge and I have a positive charge. And those particles are arranged near each other. Oftentimes, there's going to be a variety of them. So we'll actually get a lattice structure where these positive and negative charges are going to be around each other. And this results in a really high strength bond. So this is the strongest type of force. So that's not an intermolecular force, that's an intramolecular force. And this creates solids that are very high melting points. All right, so then if we have a covalent bond instead, something like chlorine to chlorine, we're really not going to get too much separation of charge. So instead of chlorine to chlorine, I want to do hydrogen chloride. Oh, she's getting frustrated. So we won't get a full positive charge, maybe a partial positive charge and a partial negative charge. And as we saw in like the molecular polarity simulator, we get a molecule where there's some distribution of charge, but it's shared between the two molecules. Then we get into these intermolecular forces. These are the types of forces that can exist between molecules. Let's start with this dipole-dipole attraction first. So with hydrogen chloride, we have that partial positive and partial negative charge that I'm going to indicate here with these delta symbols. But because there's a partial negative charge that can exist on one end of the molecule, if we have multiples of these hydrogen chloride molecules in solution or like in a gas phase, they're going to orient themselves so that they are the negative sides are towards the positive sides. And this is known as a dipole-dipole attraction because the overall molecular dipole goes this direction, and then we have another one that goes that direction. So that's why it's called a dipole-dipole attraction. There is a specific case of this where we have one of the atoms is nitrogen, oxygen, or fluorine that has a free lone pair. And this results in an even stronger attraction than a regular dipole-dipole. So when we have a nitrogen, oxygen, or fluorine, and it's having an intermolecular attraction to another molecule of the same sort, where the fluorine is near a hydrogen or a nitrogen's near a hydrogen or oxygen's near a hydrogen, and they have to be in a line. It's an interesting thing. They have to be 180 degrees away from each other, so it can't be at an angle. You get a really strong attraction called a hydrogen bond. So hydrogen bonding is what gives rise to the properties of ice and the properties of water. It's the reason why protein structures stay together. It's why DNA bonds, it's why the bases in DNA base pair with each other. And there's a lot of other reasons why it's important to learn about hydrogen bonding. So it's what gives certain things where you would think would be a gas, like water, it's a very small molecule, H2O. And H2S, hydrogen sulfide, is a gas at room temperature, whereas water is a liquid at room temperature. And the reason why water is a liquid is because it has hydrogen bonding, whereas hydrogen sulfide doesn't have that. It does have dipole-dipole attractions, but they're weaker. So it can cause the raising of the boiling point of a substance. Okay, and then the last type of intermolecular force is a dispersion force, where even like for a molecule such as fluorine gas, F2, you can get a temporary dipole that occurs where occasionally, some of the electrons will go to one end and the other electrons will go to the other end. And although this doesn't seem like this would happen that often, these small forces called dispersion forces will add up over time and result in some properties. I mentioned protein folding up above. I think I actually meant to say that here, because protein folding has these. So a protein is a very large molecule, biomolecule, where there's lots of atoms in it. There's over 1,000 or 10,000, depending on how big the protein is. So there's going to be a lot of these like dispersion forces that occur in the center of that molecule that fold it in a specific shape that give it its properties. So dispersion forces add up, and they're very weak with time. Or they're very weak, but they add up over time. So I'll just say that this one is third strongest, fourth, so let's say second weakest, and then weakest. So let's take a look at how to recognize hydrogen bond acceptors and donors. I think this is useful. And if you've taken some biology, you've already somewhat done this. So these are the 4 bases for DNA: adenine, thymine, guanine, and cytosine. And then if you're studying RNA, you'll have uracil instead of thymine. And in DNA, adenine, this base, will pair with thymine because there's 2 spots that there can be a hydrogen bond. And then guanine, this base here, will base pair with cytosine, and there's 3 spots you can get hydrogen bonding. So let's look at how we can recognize where a hydrogen bond might occur. Well, we have to add in some lone pairs, because when I pulled this image from the book, it didn't have the lone pairs here. So let's go ahead and add those. And then some of the bonds aren't shown. So there's a bond here between hydrogen and carbon, nitrogen and hydrogen, and carbon and hydrogen. And then the 2 hydrogens here, they're not bound to each other. They're 2 hydrogens like that, right? So it's kind of a shorthand notation. So I'm going to go ahead and just add the lone pairs to the rest of this molecule. And then these bases will be attached to the rest of the nucleotide, which is a sugar, a carbohydrate. And then on the end of that, there'll be some phosphate groups. It's overall a very big molecule. And then DNA is even a bigger molecule. It's a whole bunch of these connected together. All right, so I got these lone pairs here. Now, we got to look for nitrogen, oxygen, and fluorine. Well, there's obviously no fluorines here. Well, we have a lot of nitrogens, and these nitrogens can be hydrogen bond acceptors because they have a lone pair. And they can also be hydrogen bond donors because they have a hydrogen attached to them. All right, so the hydrogens have to be attached to the nitrogen. So we're not going to care about any of the hydrogens that are attached to the carbons. These aren't going to be what we're looking for. So I don't know if I want to can't cross them out. Maybe I just want to use yellow here to indicate, which of the hydrogens here we need to look for. So I'm just going to do it like this. So I'm going to look at these hydrogens, and then we can look for maybe this hydrogen's over here. And then we can look for the nitrogens that can accept a hydrogen. I'll put those lone pairs here in pink. So this is one way you can look for the hydrogen bond acceptors in pink and the donors in yellow. All right, so maybe you can try that with the other ones, and then I'll fill them in here. All right, so on thymine, there's a hydrogen bond donor here, hydrogen bond donor here, and then there's a couple acceptors. So these lone pairs can accept, these lone pairs can accept, and then these lone pairs can accept. All right, for guanine and cytosine, I'll start here with the acceptors. And then we can look for the hydrogen bond donors. So any of these hydrogens. Okay. All right, so why do A and T pair up, and why do G and C pair up? Well, A and T pair up because of just the orientation in which these are. So I have, and I'll write this in red here. So this group up here will pair up with this oxygen over here because it has a hydrogen bond donor, and this one has a hydrogen bond acceptor. And then if you think about this adenine being flipped, and this side pairing with this side over here, this nitrogen has a acceptor, and it will accept this hydrogen over here. And then that's the only ones that will pair up, because if we look at this carbon right here, this can't participate in hydrogen bonding. And then we have this nitrogen down here, which could potentially receive this nitrogen over here. And in some situations, this adenine base will flip, and you can actually get a different type of base pairing. It's called, I think, Hoogsteen base pairing, where this nitrogen and this nitrogen will this one will base pair over here. So I'll call this like 1 prime, and then this will be 1 prime, and then this nitrogen can pair over here. So 2 prime, 2 prime. All right, so those are some unusual base pairing situations. And then guanine and cytosine, these will have 3 hydrogen bond pairs each, or as a group. This oxygen can easily receive these hydrogens over here. So this is 1 and 1. And then this hydrogen over here, we can see will intermolecular force with these lone pairs. And then these hydrogens over here can have an intermolecular attraction to these electrons over here. And I believe there are also some alternate pairing situations for guanine and cytosine. And we can see that there's a hydrogen bond acceptor and a donor on the bottom portion of guanine. And there is one hydrogen bond donor over here. So there could be some alternate base pairing as well. But we can see the most common ones listed in this image here. So the G and C, guanine and cytosine, have 3 hydrogen bonds, which are drawn here in red. And these are not, there's no electrons in that bond. It's just a electrostatic attraction, or a partial electrostatic attraction between the lone pair here and the partial positive charge on the hydrogen here. And it's really kind of like a 3-atom partnership where you have a nitrogen, hydrogen, nitrogen, oxygen, hydrogen, nitrogen, nitrogen, hydrogen, oxygen. And in order for DNA to unfold, you need to apply heat, and in order to break these pretty strong hydrogen bonds. And then at A and T, they just have the two hydrogen bonds here. And I think I just kind of summarize that here. One thing you always hear about with DNA is it's a double helix. So you have these nucleotides will wrap around, and you'll get one strand that will go down, and then you have one strand that goes up. So they're running in opposite directions. And I thought that would be kind of interesting to talk about for a little bit. All right, so I have a bunch more practice problems to go over with you, and you could work through these and just try them on your own. And then if you want to watch the video, you can see how I do these ones. These will take me a while to do, so feel free to stop the video and try these on your own. You will get practice with this on active chemistry, but I think drawing these by hand, practicing them, will get you ready for the exam. So, all right, I'm going to start here with this tellurium hexafluoride molecule. I think it's one of the easier ones on this sheet. I don't even know where tellurium is on the periodic table, so I'm going to have to look that up. Okay, so it's below oxygen. So it's down here. So it's going to have 6 valence electrons, and then fluorine will have 7 each. All right, 48 electrons. Oh, I can put it over here. So I have this sheet, so it kind of breaks this all up. Now this class is going to be, the class number is the X notation. So this will be an AX6 class because there's already 6 atoms, and I'm not going to give you any exceptions like the AX7 and so on. So it would have to be AX6. The steric number is just the M plus the N. So that would be 6 in this case. And then the shape is going to be based off of the information from above, which I think I can... just give me a sec. So even without drawing the structure, you can figure out what the shape and the angles are going to be. So this is going to be octahedral, and it's going to be 90 degrees. Tellurium goes in the middle, and then we have 6 fluorines around it. Okay. And then that uses up all 48 electrons because each of these fluorines has 8. So 8 times 6 is 48. All right. Next one is iodine tetrafluoride cation, which means we have to subtract 1 electron. 7 times 5 minus 1 is 34. Now, for this one, it might be a little tricky to know what the X notation is right off the bat. We know that it's going to be AX4, and then there might be, we don't know how many electrons quite yet. Well, when I do these ones, I know that fluorine is going to have an octet. And since there's 4 of them bound to the central atom, I know that I have to have at least 7 8 times 4, or 32 electrons. That's going to leave me with 2 electrons left over. So in that case, it has to have 1 lone pair. So this will be an AX4E class, just based off of that quick, mental math that I'm doing in my head. And then we can verify that by drawing the Lewis structure. Now, if it's AX4E, this is going to be a seesaw shape. And, you just find 4 and you find 1 here. This steric number is 5, meaning it has a trigonal bipyramidal electronic geometry. But what I want to know is what's the shape? It's a seesaw shape. And then here are my angles. Okay. And it won't less than 120, less than 90. And then for this, the way I'm going to draw seesaw shapes is by removing one of the equatorial atoms. And I'll put a lone pair there. I don't like how that looks. And where does the positive charge go on this? Well, the positive charge is going to go on the atom that's got the formal charge that's positive, which will be the iodine here. The formal charge for that will be 7, which is the valence number of iodine, minus the 2 lone pair electrons, minus half the numbers in the bonds, which gives us a positive 1. So we can indicate like that. Ga is gallium, and gallium on the periodic table is below aluminum. It was one of the elements that Dmitry Mendeleev predicted when he formulated the periodic table. So a very low melting point metal. So it has a melting point around 30 degrees. If you put it in your hand, it'll actually melt. So gallium trihydride or triiodide is going to have 3 plus 21 or 24 valence electrons. Since each of the iodines has to have an octet, this is going to be an AX3 class. We're not going to have any lone pairs left over. And also gallium is going to follow that same rule that aluminum does. It's going to be an electron deficient element. It's okay that this one will only have 6 total electrons. So we'll put gallium in the middle. This will be 3, and this will be a trigonal planar shape with 120 degree bond angles. So we'll draw the iodine above or below, it doesn't matter. We can just use that Y notation. Everything's 120 degrees apart. And then we're done with that. All right, so some of these are going to start to get a little bit trickier. We have bromine and 2 fluorines bound together. This will be 7 times 3, and then we need to add 1 because it's got a negative charge, so 22 electrons. And then my trick for doing these, again, I have this halogen. It needs to have 8 electrons, so we're going to have 16 distributed to the fluorine, and then 22 minus 16 gives me 6 electrons left over, meaning I have 3 lone pairs. So that means this notation is going to be AX2E3, which is a linear geometry where we remove all the equatorial atoms from that trigonal bipyramidal electronic shape. And this ends up giving us bond angles that are 180 degrees. We can look back at the cheat sheet, just to kind of verify that here. So we have 2 and 3 linear, 180, And there's a couple examples over there. So bromine goes in the middle. We have fluorines on opposite ends. And then we have the lone pairs. And then there should be a negative charge somewhere. The formal charge on this bromine is going to be 7 minus 6 lone pair electrons minus 2 total electrons. I guess there's 4 being shared, so half that is 2. That gives us a -1 charge. So we can put the negative charge right there on the bromine. This next molecule is going to be an interesting one to try to draw. A lot of the problems in your textbook use these types of examples. So selenium, this is below sulfur. It's got 6 valence electrons. Then oxygen's got 6, and then chlorine has got 7 each. So we'll have 12 plus 14, which is 26. We'll put selenium in the middle because it's the less electronegative of the 3 atoms. And the notation here, the class, is, well, there's going to be 3 atoms bound to the selenium. And then if we put 8 electrons on each of those, that'll be 24. And then we're going to have 2 left over. So then it's going to be AX3E. So that's the kind of way I start by trying to figure out what that class is. But you can start by trying to draw it and drawing the Lewis structure and then seeing how many electrons that you're going to need. So what I'm going to do is note that, well, I'm going to have a lone pair somewhere. So I'll put the lone pair on the top. And then we're going to have the wedges and the dashes. So I'll put the chlorines on those. Doesn't really matter. And then we can put the oxygen over here. But remember, oxygens, they like to have 2 bonds, or they like to have a double bond. So what if I put a double bond here? Well, steric number is 4 because it's a tetrahedral shape, or electronic geometry. The shape is trigonal, pyramidal. And the angles here are less than 109.5 degrees. The exact number is not important. But what we want to double check here is that our formal charge is correct. Well, selenium, it's got 6 valence electrons. So 6 minus 2 minus 1, 2, 3, 4 is going to give us a formal charge of 0. And then this does indeed work. It's very interesting to see something along this lines. Oxygen cannot do this because selenium is in the 3rd row. Actually, it's in the 4th row of the periodic table. So selenium can access those d electrons because we have 2, 4, 6, 8, 10 electrons on that central atom, which doesn't occur with stuff like oxygen. So we could never see oxygen like that. But selenium can do some cool things. All right, the next one is chlorine trifluoride. Here we have 4 times 7 or 28 valence electrons. The chlorine is going to be in the middle, and if we give 8 electrons to each of the fluorines, we'll be left with 4 electrons left over, meaning the notation is going to be AX3E2, and we can go and we can look at what that should be. Well, that's going to be a T-shaped molecule. AX3E2 is T-shaped. Bond angles here are going to be less than 90, less than 120. And we can draw T-shaped a couple different ways. I I think up above we talked about how it's not quite up, but maybe at a slight angle. And then we'll put the two lone pairs on the chlorine in the middle, where fluorine can never have more than 8 electrons, but chlorine can. And we can double check that the formal charge is correct. That's what I always like to do. So chlorine is 7 minus 4 minus 3 is 0. Okay, so that's good. Phosphorus trifluoride is going to give us a total of 21 plus 5, which is 26 valence electrons. Give 8 to each of the fluorines for a total of 24, leaving us with one lone pair left over. That's AX3E, which is a trigonal pyramidal geometry. Phosphorus in the middle, and then 3 fluorines on either side. So we've upgraded from our Lewis structures towards these more sophisticated three-dimensional shapes. Oops, so not hydrogen. And having a model kit is pretty helpful for this kind of stuff. So maybe, if you're still, you can find model kits online, or you can build your own. With the lab kit that we have, you build your own model kit. So use that when you're trying to learn this stuff. So the next one here I have is IO2F2 minus. Here we have kind of a similar looking thing that we're going to get for the selenium. So for each of these oxygens, we can think about putting a double bond anytime we have an oxygen like this. So that's what I'm going to do for this one. Let's start by finding how many total valence electrons there are. There's going to be a lot here. So 7 plus 12 plus 14 plus 1, 34. Okay, we have 4 atoms, so 4 times 8 is 32. Okay, so we're going to have one lone pair on the iodine. So this will be a new notation. This one's AX4E, and AX4E is square pyramidal. Or we can put the lone pair on the bottom or on the top. Put it on top, doesn't matter. And did I say square pyramidal? That's wrong. It's not that. It's where is it? 4 and 1. Is this seesaw? Yeah, it's a seesaw. Yeah, so it's going to be similar looking to this one up here. So if it's seesaw, I can't write seesaw. I like to draw it with the lone pair here and these two up and down. In this case, we can think about where the oxygens are going to go and where the fluorines are going to go. I'm trying to remember what the correct answer is for this one. There is a correct location for them, and I think the fluorines go up and down. This is a very hard molecule to draw. Okay. There is a rule for why the fluorine goes up and down. I don't remember what it's called. Not a big deal. Not for this class, at least. All right, and then Here we're going to have a negative charge on the iodine because it's got quite a few electrons. It's got 2, 4, 6, 8, 10, 12, 14. 14 electrons packed on there on that iodine. 7 minus 2 minus 1, 2, 3, 4, 5, 6. Yeah, it's going to give us a -1 charge. The bond angles here are less than 90, less than 120. Difficult molecular. Next one, xenon oxo tetrafluoride. Xenon forms some compounds. It's one of the more unusual noble gases. There's a cool inner chapter on noble gases. You can learn more about the xenon compounds and how to draw them. So 6 for the oxygen and then 7 for each of the fluorines. 42 valence electrons, a lot. So if the oxygens and the fluorines each get 8, that's going to leave us with 2 left over. So this is the AX5E. This is the one I was trying to do for the last one. This is square pyramidal. Bond angles here are less than 90 degrees. Xenon's in the middle. And then for this one, there are 2 ways we could draw this structure. We're going to have the lone pair on the top, and I'm going to put the oxygen here on the bottom. So you could think about where the oxygen wasn't on the bottom, and then it was on one of these other locations. But in this case, I think the oxygen goes down here. It's kind of hard to know. So if you drew it the other way, doesn't matter. It's hard. You can't predict that. Yeah, I might have gotten these mixed up. Let me look this up. I'm having a hard time finding it, so never mind right now. Okay. Last 3 examples I have. This one, I think we've done this one already. This is similar to carbon dioxide. Germanium is below carbon. And we're going to have a total of 16 valence electrons. For this one, if we try to give each of the oxygens 8 electrons, we'll be left with no lone pairs. And then the germanium won't have a full octet. So we have to do double bonds here. And because there's 3 atoms and this is just going to be our AX2 notation. This is a linear molecule with 180 degree bond angles. And then these last 2 examples are molecules that will have resonance structures. And now that I'm thinking about it, this molecule here also has a resonance structure. Because one of the rules I was talking about in the last lesson was for Lewis structures, we want to put the negative charge on the more electronegative atom. So which one's more electronegative, oxygen or iodine? Well, I'm fairly sure it's oxygen, right? So the negative charge isn't going to really want to be on the iodine here. Instead, it's going to want to go here, like so. And when we do this, we get a pair of resonance structures. Where I just need to okay. Yeah. So this is the more correct structure. And these are very difficult examples, which is why I'm doing them with you. And I think when I did that, did I move everything? Let's move over. Must have moved over. Okay, there we go. Carbon trisulfide. All right, so this one we have carbon with 4, sulfur with 6 each, and then the 2 minus means we add 2 electrons, so 24 valence electrons. Carbon can never have more than 8 electrons. So this is a case where we're not going to have any lone pairs on the carbon in the middle. So there's no tricks on this one. This will be an AX3. And the carbon will have to be double bonded to at least one of these sulfurs so that it can have an octet. So we don't put lone pairs on carbon. And the 2 negative charges come from the fact that each of the sulfurs is going to have 3 lone pairs, or 2 of the sulfurs will have 3 lone pairs, and 1 will have 2 lone pairs. So this will be a negative charge here, this will be a negative charge here. So what we're going to want to do here is draw 3 total resonance structures. And then this one here, just rotating each of these around. So resonance structure 1, 2, and 3. This is a trigonal planar geometry. Whenever we figure out the electronic geometries, if it has a double bond, remember that just counts as one bonded atom. So this counts as one steric group. So the 3 steric groups are the 3 atoms attached. Bond angles here are going to be 120 degrees. And the bond lengths will all be equivalent because of the resonance structures. All right, our last hard example here is IO2 minus. And this will have a total of 20 valence electrons. And each of the oxygens will need 8. So we're going to have 2 lone pairs that we need to put on the iodine to distribute those remaining 4 electrons. So this will be an AX2E2 class, which is the shape that water has. So this is a bent shape. And the bond angles here are going to be less than 109.5 degrees. So we'll draw this like it's water. And then what am I doing here? I'll put 2 lone pairs on the iodine. And the interesting thing here is these oxygens, we can put the double bonds here like this. If we do this, we'll get the iodine that has the negative charge. Because I can go ahead and put these lone pairs here, show you. If we do the formal charge on this iodine, it'll be 7 minus the 4 total lone pairs minus the 4 electrons that are the half number of these. It gives us a -1 charge. But we want to put that negative charge on the more electronegative atom, which are the oxygens. So we'll have 2 resonance structures. We'll have this one. And we'll have the other side. All right. Well, there we have it. Lots of example problems today. And I think that is really what it comes down to for a lot of chemistry, is that you just need to practice. I know how to do a lot of this stuff because I've just done a lot of practice over the years. Done this worksheet a couple times, so I did go through it very quickly. Feel free to reach out if you have any more questions. The next lesson will be an optional one. If you decide you want to watch it or read through the chapter and do the practice problems on active, you can get some extra credit towards your homework grade. And I think it'll be really interesting, so I encourage you to watch it if you have time. Take care and have a great day.